Okay, then I welcome you all to the last session of this conference in the research track. And we will start by having a talk from Josef. Here he is the co-founder and CEO of Ackee Blockchain Security, and he will give a talk on fuzzing Ethereum smart contracts.
Okay, thank you very much. So let's deep dive a little bit into fuzzing. Before we start, I'm Josef, and we at Ackee are smart contract auditors, but besides auditing, we are putting a lot of effort on education and also tooling. So with the tooling, we can create some open source, and with the open source, we can move some things forward, such as fuzzing. So I'll show you first of all something about fuzzing, and then I will show it on our tool. And we can be doing such nice projects thanks to our clients and also foundations who supported us by grants. So big thanks to Lido, 1inch, Safe, Axelar, or Solana Foundation, Coinbase, and Ethereum Foundation. So Fuzz Testing, there's been recently kind of like a lot of buzz on the Twitter, and it was a beef between formal verification and Fuzz Testing teams. What I missed there always was that, for example, when someone from the formal verification team compared to fuzzing, they use like very old fuzzing techniques for the comparison. So it came to my mind that it would be nice to a little bit categorize and describe what fuzzing could be about, because then we can be comparing like contemporary Fuzz Testing with contemporary formal verification. Because Fuzz Testing is a technique that stands somewhere like here in the pyramid, where we represent the cost, which is the complexity of doing the task, and impact, which means like how harmful it could be. So of course, like in the very basics, it needs to have a good code quality. Then there are some very low-hanging tools like static analysis, like the demo talked about in the morning. Then of course, like the necessary thing is to have like good integration and unit tests. And fuzzing is somewhere that not many teams are using by default. So, but it's still something that is accessible without paying for an audit. And of course, the audit, that's the manual review, which is like top of the iceberg. That's the most expensive thing. But if the parts before that are rotten, then the audit doesn't save the code quality. So it should like build one step after another. Fuzz tests often are written by auditors. Sometimes are written even by the team. Our motivation is that the team should be writing Fuzz tests as well. And so maybe you don't know what is a Fuzz test. So I guess you know, but just it's like testing random functions with random parameters on inputs. You can understand a very simple example as if you go to the bartender and tell him, hey, give me 1 beer, then you go and tell, give me 2 beers, then you go and tell, give me 100 beers, then you go and tell, give me 0 beers. This is Fuzz testing. So it's the easiest way how to explain it. And there are some categories. So first, I would like to define the difference between stateful and stateless Fuzz tests. So stateless Fuzz test is the one where basically the fuzzer doesn't remember what happened in the previous step. So each test cases are independent, and if we compare it to this bartender example, it's like every order at the bar is independent. So the bartender doesn't remember that you have been to him 100 times before. Of course, the reaction would be different if he would remember, which is stateful Fuzz testing. Here, basically the fuzzer remembers what happened before. So you can build the test cases one after another. In case of smart contracts, by some transaction, you move the state of the system to some state, and then you test after this state. So this is stateful Fuzz testing. Of course, stateful Fuzz testing is the thing you want to do with the smart contracts, because smart contract states changes by transactions, and you want to be chaining the transactions in the test to get to some undiscovered state. So that's the first category. The second category is about the knowledge of the system, where the original fuzz testing technique is called black box fuzz testing, and this is something that a lot of times as I said, the formal verification guys are comparing formal verification to. This is the original fuzz testing technique, and it means that the fuzzer has zero information about the code. But when the code is simple, such as in this case, it's not really hard to explore all the states by brute force. It's doable, it's okay. But the contemporary blockchain systems, smart contracts, are very complex, a lot of integrations, and of course it's not simple as this, which means if you run black box fuzz testing, the fuzzer usually gets stuck in some space where there are no issues at all, and it would not discover the issues because it would take, even on the current hardware, ages to get there because the state space is too complex. So it's not possible to do a proper fuzz test of smart contracts by just running black box fuzz testing. The solution to this, of course, is something that's called gray box fuzz testing. The definition here is not very clear, so I a little bit define it as the fuzzer has some information about the tested system. And in this definition falls, for example, property-based fuzz testing, which is something that, for example, Ackee is doing. And it's a fuzz testing technique where the tester introduces something called invariants. And invariants are basically conditions that cannot be broken. So it could be, for example, the balance of the address of the smart contract cannot go below 0, or in the case of the bar, the cash in the bar cannot be lower at the end of the day than it was in the beginning of the day. So these are the easy conditions that the tester defines, and in that case it's not pure black box testing, it's gray box testing. Second example is something that's called coverage guided fuzzing, which means the fuzzer is by some heuristics getting information about the visited states and is trying to readjust where to go next. So there is some information about the tested system. And of course, the, let's say, extreme case is that is white box fuzz testing, where the fuzzer has all information about the state space. This is something that would be very nice if, for example, AI could do, but we are not there yet. So right now, white box fuzz testing can be achieved only by a tester who understands the contract and is helping the fuzzer. And I will show you what it means later. So that was the main categories. Now we are going to deep dive a little bit deeper. These are a little bit edge cases, but for the case of smart contracts are very essential. This technique is called differential fuzz testing, and basically here we can compare the outputs of two different systems and see if they match. And the first system is the tested smart contract, and the second system is some reference implementation. So for example, here is a formula for counting continuous compound interest, which was used in one protocol we audited. And this was implemented in Solidity by the team. And what we did is that we implemented this formula in Python, where it's very easy to implement such things. And then we just run the fuzzer, and the fuzzer was shooting the same input data to our reference implementation and to the tested smart contract. And of course, in some cases, it started returning different results. So we looked at it, and it was because of some rounding errors in Solidity, which would be extremely hard to discover by just manual code review. That would have to be really a genius auditor to find out. Here, it's very easy. So this is differential fuzz testing. Next advanced technique is called fork fuzz testing, and it's again very essential with smart contracts, because today smart contracts depend heavily on integrations. They are not like isolated contracts, but interact with other contracts, such as oracles or price oracles. So for example, Aave or Chainlink. And if we would be testing the contract without the integration, we would have to implement some kind of like mocked data, and it's not sufficient because the mocked model is very simplified. So we don't want to be testing with mocked data, we want to be testing with the real world data. And for that, we need to fork the chain and have like a local deployment, which is testing then on the real world data. And this is something that, for example, is again very hardly achievable by formal verification because they have to be mocking and we can be testing on the real data. And so these are the main categories. And what we did is that we tried to define basically something that highlights that the fuzzing has moved to another level. And we describe that as manually guided fuzzing, which basically means that the dependence is more on the testers, which means the tester is responsible for searching the state space, and the fuzzer is just like a tool that allows that. And we are doing this by implementing invariants, which already existed, and we added something that we call flows. What is a flow? Flow is basically defined sequence of single actions, and it's defined by the tester. So the fuzzer then is running and is trying to break the invariants, as it was in the case of black box testing or gray box testing, but on a defined basically pathway using the flows. I can give a like crazy example. The defined flow would be go to the bar, order some random number of beers with the first bartender, then go to the second bartender, or order some random number of beers. That's the defined flow. If we don't have this flow and just keep the invariants that we cannot break the cache to go below 0 or something like that, and let it to test as a gray box testing, the flow would be, I don't know, lay on the floor, open the doors, and do all the crazy stuff, but it would never get to the actual test case we want to do, which is test the 2 bartenders. So this is something like that very simplifies the problem, but puts the responsibility to the tester / auditor researcher. And it actually means that the fuzz test is the code that we write. So it's a like very long test case where we are trying to think about all possible cases and just like are fuzzing around them, not like fuzzing everywhere. And by this, we are able to run the fuzz test in case of like minutes, not like days or years. And how does it look? So we have the framework for that, which is called the framework. And invariant is like very easy two-liner definition. So it's basically like an assert. And the flow is easy as this, like 3 lines, which does basically how should the functions be called in which order. It's in Python. And I mentioned the Wake framework. So Wake framework is the framework that we've built. It's open source. And we have built it because we were not able to do all this magic in the existing tools. And Wake framework supports all of this. And on top of that, there was a talk by Demo in the morning. So Wake has a static analysis, such as Slither. Then it has a testing framework. There is a debugger. In the testing framework, you can be writing as a developer like normal unit integration tests in Python, but also writing the fuzz test in Python. And by writing fuzz test, we mean manually guided fuzz test. And there's also a useful extension as a front end for that. How does it work? It kind of works. We have already discovered some issues with purely the testing framework. So we have been collecting this since 24. So these are the discoveries we had in this year. And it's public on our GitHub. If you're very interested, a lot of the issues have links to the exact test case. And yeah, if we compare Wake framework with other existing frameworks, so we try to build something we call a Swiss knife. So it allows to have the static analysis, testing framework, fuzz testing framework, and language server all in one tool. But it's for Python Max 6 as we are. And if you would like to try the front end from Wake, it's this extension for VS Code. So basically, by installing the extension, it also installs the Wake, and you have it visually in the VS Code. And if you would like to explore Wake, it's getwake.io. And if you have any questions, I'll be here after the talk. Thank you.